Today, I will introduce simulated annealing optimization. Uh, it is a method inspired by the cooling process of metals. It is used to find good solutions for difficult optimization problems. Annealing is a heat treatment process used for metals and solids. The material is first heated to a high temperature and then cooled slowly. This slow cooling helps the atoms arrange themselves into a more stable and lower energy structure. In simulated annealing optimization, the algorithm sometimes accepts a worse solution during the search process. Uh, this helps the method escape from local minima and continue exploring the search space to find a better solution, or in the other words, we can say to find the global optimum solution. In this slide, we are going to get familiar with the control of annealing process. The acceptance of a new search step is decided by metropolis criterion. Assume the change in the objective function is called delta, and if delta is less than 0, the new solution is better. So the step is always uh, uh, accepted. But if delta is greater than 0, the new solution is worse. So it may still be accepted with a criterion probability. A random test is used to decide whether this worst solution should be accepted, and this helps the algorithm explore more solutions and avoid uh, uh, we get stuck in local minima. In the next slide, we can see the temperature uh, and the cooling schedule. Temperature T, here we can see, is an important parameter that controls the behavior of the algorithm. When T is high, the method is more likely to accept worse solutions and explore widely. But when the process continues and the temperature Tk is gradually reduced, this makes the algorithm more selective and focused on improving the solution. At each temperature level, the algorithm performs a fixed number of search steps, here denoted by LK, before the temperature is reduced again. And the overall strategy for choosing how temperature decreases and how many steps are done at each level is called the cooling schedule. This cooling schedule strongly affects the performance of the algorithm in optimization process. Here we want to explain the steps of the simulated annealing. Step 1, define the optimization problem. First, the optimization problem is defined by specifying the objective function. Suppose that fx is the objective here, decision variables and constraint that we have. The objective can be minimized or maximized anyway. Then after that, we have a step 2, generate an initial solution. In this step, a feasible initial solution like x0 is selected as the starting point of the search. It can be randomly generated or obtained from an existing method. Then we have step 3, set the initial temperature. An initial temperature T0 is chosen. We should notice that a high temperature allows the algorithm to explore the search space and accept worse solutions more easily. Then we have step 4. In this step, we evaluate the objective functions. Then we have step 5, generate a neighborhood or a neighboring solution. In this step, the new candidate, we call it X prime, is created by making a small random change to the current solution. Then we have step 6. We evaluate the neighboring solution by the objective function. So it means that we calculate fx prime. Then we have apply the acceptance. In this step, we apply the acceptance criterion. So if the new solution is better, it is accepted. If it is worse, then it can be still accepted, but we have a probability function here. It's a function of the exponential, as you can see here, e to the power of minus delta over t. And this probability function allows the algorithm to escape local optima. Then we go to step 8 and update the current solutions. If the new solution is accepted, it replaces the current solution, and otherwise the current solution remains unchanged. Step 9. In this step, we record the best solution. The best solution that we found during the optimization process is stored for the final result. Then we have a step called thermal equilibrium, or step 10. In this step, we test several neighboring solutions at the same temperature. Why? The reason that we do this is that we are going to sufficiently explore the search space, and we want to make sure that we are selecting the best solution before we decrease the temperature, or in the other words, before cooling. Then we have step 11, reduce the temperature. The temperature is gradually reduced using we call it a cooling schedule, like T new, or the new temperature, is a function of the old temperature multiplied by alpha. This reduces the probability of accepting worse solutions. Then we will have in step 12 the stopping criterion, and then there we check this criterion. The algorithm stops when the termination condition is reached. It could be this termination condition could be a minimum temperature, I don't know, maybe maximum number of iteration, or even it could be further improvement. And so then we can repeat it from the step 5, generating a neighboring solution. This is a step-by-step explanation of the annealing simulation. In this example, simulated annealing is applied to minimize the objective function. Z equals x to the power of 2 plus y to the power 2 with bounds -3 to 3 for both x and y, the decision variables, and the expected optimum for this function, which is a minimum, is 0, 0, x 0 and y is 0, and the value or the objective for this node, for this 0 and 0, would be 0, as we can calculate it easily. Here we can see the options that we have for the simulated annealing syntax. You can see here the first one, the display, and this is the first option, and it prints the progress information at every iteration. The max iteration, it is defined 500. It stops if the algorithm reaches 500 iterations. Maximum fun evaluations, 5,000 here, the number is adjusted. It stops if the objective function is evaluated 5,000 times. Initial temperature, 10. Set the starting temperature. If it's high, it means more random exploration at the earliest stages. Then we have temperature function. Use an exponential cooling schedule to reduce temperature over time. Then we have re-annealing interval. This is for rescaling step sizes every 100 iterations to improve exploration. It is something not related to the standard simulated annealing. It is something added to this one, and it's a kind of simulated annealing that improved. Then we have annealing function. It is used Boltzmann annealing for generating new candidate points. Then we have tolerance function. It stops if improvement in the best objective value is smaller than 1e minus 12. And then we have plot functions, which provide some capability for the display of the plot. Thank you for attention to the content of the course. For future contact, you can visit our website with the address of smartest.dtu.dk, and you can visit our website.